Welcome back. Today's topic is analog to digital conversion. In the last video lecture, we have discussed about digital to analog conversion. We have seen that two types of digital to analog converters are widely used. One is weighted resistor DAC, the other one is R2R ladder DAC. And we have also seen that unlike the weighted resistor DAC, which requires different types of resistors and that too with higher accuracy, the R2R ladder circuit, it requires only two types of resistors and is highly advantageous when the number of bits is higher. In today's class, we will discuss about analog to digital conversion, and we will see different types of analog to digital converters. So I hope that by the end of today's lecture, you will be able to compare the operation of different analog to digital converters. We call them as ADC. So I hope that you will be able to compare different ADCs based upon their operation, and I hope that you will be able to design suitable ADC corresponding to given analog input conditions. Okay, so coming to the contents, I will start with what is the requirement of ADC, and I will go with the types of ADC, and in detail we'll discuss about the operation of these three things and followed by problems on these converters. Coming to introduction, why do we require digital data all the time? As already said in the previous lectures, you know that every physical signal basically, it is an analog signal. So the thing about analog signals is that they are very infinite in nature. And if we see our ears, we do hear infinite sounds, we can see infinite colors, we can have infinite smells, but there are infinite numbers between 1 and infinity. On the other hand, digital data deals with only discrete or finite signals. In particular, dealing with infinite number of analog data is very difficult. As already said, analog data will be up to infinite. You are supposed to mention them from 0 to infinity. And it is very difficult for us to store and even very difficult for us to process this huge data which is extending from 0 to infinity in terms of representation. This is where the analog to digital converters come into picture. An ADC, which you call it as an analog to digital computer, it converts any analog signal to quantifiable data. The quantifiable data, which we call it as digital data, it will be easier to process and also for storage. And mostly it is very accurate and reliable also when compared to your infinitely extended analog data. Your digital data will be mostly in terms of your 0 or 1. So this is your representation of an analog to digital converter, where you do take analog input and you convert it into digital output. So how much bits will be there in the digital data depends upon the size of your analog inputs. And the device which is generally used, it is called as A to D converter. In short, we will call it as ADC, analog to digital converter. In practice, we do employ different types of ADCs. The first one being the counter controlled converters, normally called as counter type ADCs. The second one is a dual slope converters, and the final one is the parallel comparator converters. In other words, it is called as a flash type of ADC. These three are the widely used ADCs in our digital LS. As already said, your voltage or current, it will be having some minus infinity to plus infinity values, right? You can't store these values directly, and it is a very difficult thing to store. So that's why if you convert the data into digital data, then it can be represented as 0 and 1 and can be stored very easily. So that's fine. We do employ ADC converters because the data will be processed in digital means only. So we will employ any of these three converters for conversion of analog to digital data. So now we will discuss each of this operation in detail. The first one is the counter controlled ADC. The counter controlled ADC, often called as counter type ADC, the major components include a binary counter, a DAC. See, ADC requires a DAC also in this one, and an analog comparator. So the output of DAC is VC. Sorry, this is VC, which is equivalent to corresponding digital inputs to DAC. That we will discuss in detail. So try to remember the important components: a binary counter, a DAC, and an analog comparator. These three are the important components of counter type ADC. Now this is the circuit arrangement. If you carefully see, this is your counter, binary counter, what we have said, and this is a DAC, what we have discussed, and this is an analog comparator. So if you carefully see, this is your analog input. Let us suppose this is my analog input, which is to be quantified. Now this, with respect of your sample and hold circuits, it is being fed here. Here it is compared with a VC, often called as a control voltage. This control voltage, it comes from here. This I will explain it later. But see here, VI and VC. See, if VI is greater than VC, which means your input is greater than your control. Initially, the control voltage will be 0. Initially. So initially, this will be 0. As long as Vi is greater than Vc, your output will be 1. If Vi is less than Vc, then output will be 0. So now initially, now this is 0, right? So Vi, you are getting a maximum value. So automatically there will be a 1 here. So 1 up to here. See the clock, whatever the clock which you are giving, that will be appearing here. This is an AND gate, right? So this is already 1 now. So this is your clock. So if it is 1, then you will be getting an input. If it is 0, you won't be getting any output here. So the number of clock pulses will be appearing here. Okay. So it is just a counter which counts the number of pulses which it has received. And based upon that, the digital output will be explained. Now, see here. Once it has been done, the digital data. Now, whatever the digital data which has been received here, which has been converted here. Now, this again will be converted into DAC. Here you can use a R2R or weighted structure. So it is a DAC. So whatever the data which it is being converted into, again it is converted into analog. So when it is converted to analog, once again there will be a check here. And again, if it is greater than this one, then automatically there won't be any output here. So I will explain it once again with, I'll take an empty slide here. Now let us suppose you do have an input here. Okay. And you are giving it to your AND gate, and here you are giving, let us suppose, clock pulses. This is your binary concept, okay? And here you are getting the digital output, and again it is being fed to your DAC. And from here, DAC, you will be getting a V control voltage. Okay. Now understood. This is a simple representation. Now let us suppose if V input is 5. Okay. So if V input is 5, now initially its value is 0. Okay. Control voltage is 0. So Now what happens is, since V input is greater than this one, you will be getting a value of 1 here. Okay, since it is 1, the clock, let us suppose this is 1, 2, 3, 4, 5. Okay, see now 1, since it is 1, so automatically what happens is the output will be, for this first pulse, it will defaultly go in the binary counter. It becomes, see, initially it was 0, 0, 0, 0. Now since one pulse has got into picture, now what will happen? This will become 1, 0, 0, 0. Okay, so now if I converted this one into DAC, what will be the value? It will be 1, right? So 1, again it is compared with 5. So still this one is higher. So again you will be getting 1 only here. The output of this is either 1 or 0. So now since it is higher, I will be getting again 1. So again, since it is 1, second pulse also will go into picture. Again here, what you will be getting? You will be getting 0, 0, 1, 0. So what is this value? This value is 2. So again, since it is higher, again you will be getting 1 only. So this time again, third one will go into picture. So here you will get 0, 0, 1, 1. So this will become 3. Again it goes on checking. Now fourth one will go into picture. So now you will get again 0, 0, 1, 0, 0. This is 4. Again, see here. Since again 5 is greater than 4, again you will be going into this one. 5. Fifth one will go into picture. So again you will get 0, 1, 1. So now you have got 5 here. Again it will compare. Again, since it is equal to 5, again sixth pulse also will go into picture. Sixth one also will go. Now again what you will get? 0, 1, 1, 0. Now what is output? 6. Since 6 is greater than 5, it will stop. Okay, so this is here. So whatever the last one was there, 0, 1, 0, 1, this will be a digital output. See, for an input of 5, what you have obtained now? 0, 1, 0, 1. Right? This is the operation of this counter type. So here what is the important part? This is a comparator. This is the important one. It compares your input and also your control output, which comes from your DAC. The other one is a binary counter, which counts the number of pulses which you are getting from here. And this is a DAC. It is also one of the important components. So once your conversion is being done, what you will do here, you will be having a reset button. You will reset the thing. This is how your converter is going to work. Understood? Since it counts, it depends upon the counting of number of pulses which are entering into the system. It is called as a counter type ADC. Now, this is what is present in this figure. Now, see here, the counter is set to 0 at the beginning of each cycle, which causes output of DAC to 0, right? So VC is compared to your input voltage fed by the sample and hold circuits using the comparator, whose output will be either 1 or 0 depending upon the relative magnitudes of VI and VC. This is what we have seen, right? So you will be having a VI, and here this will be coming from your DAC, right? Right. So as long as this is higher than this one, you will be getting a 1 as an output. And if it is lower, then automatically it will move on to 0. If VI is greater than VC, comparator output will be 1, which is used to enable the AND gate. Here you will be having an AND gate, right, which is having a clock pulse. This in turn allows the clock pulses to enter the counter, right? The output of the converter is fed to the DAC, which computes a decimal equivalent of its binary inputs, right? And the output of DAC, what happens? It increases in a staircase fashion, right? And it is continuously compared, right? Initially, when only one pulse was there, your output voltage was like this, control voltage. Again, one pulse entered, next pulse, next pulse, next pulse, next pulse. It compares with your VI, right? So as soon as VC becomes greater than VI, output of comparator will be 0, which disables the AND gates and clock pulses are prevented. from entering the counter. And the output of ADC is then read from output terminals of the counter. See, this is a representation. See here, this is your, for an equivalent of 5, this has been given, right? So initially VC was 0, next 1, next 2, next 3, next 4, next 4. Right. So automatically what happens? The counter stops at 0, 1, 0, 1 because there is no further improvements. Now this is a clear representation of your, for an equivalent value of 7. Right. So this is your control voltage slowly increasing up to higher levels. Now this is a clock. How many pulses have entered? 7 pulses have entered up to here. Right. Because beyond that it is overcoming this value, so automatically what happens is there will be a cut down of the counter. So up to here, if you carefully see, you are having up to, see, this is the point where the counter stops, because what is happening here? Your VC is greater than your input voltage. This is your input voltage and this is your control voltage. Since at this point it is increasing, automatically you are getting a stop of the counter. Here again what you are doing, you are resetting the counter. This is reset. Understood? This is how a counter type ADC works. So what are the, it is one of the simplest one. So very simple in construction, easy to design and very less expensive because it requires only few components. What are the few components? A binary counter, a comparator and a DAC. And the speed can be adjusted by adjusting the clock frequency. If you increase the clock frequency, then it becomes a speedier one. And it is faster than the dual slope type ADC, which we will see in the next video. And the disadvantage, the conversion time is significant. If you carefully see, it depends upon the number of pulses which you are giving into the system, right? If the value of the analog input is too high, then the conversion time will be too high. And more importantly, it cannot sustain very high frequency inputs. There is a limitation on the frequency of the inputs. Okay, so these are the advantages and limitations of counter type ADC. I hope you have understood. In the next presentation with the flash